All right, let's resume today's lecture. Today we are going to wrap up chapter 8. We are going to talk about the exponential distribution and Poisson process. Right. I think like in general there are quite a number of properties we need to go through like in today's lecture. Some of the properties are mathematical heavy and some have very simple proofs, but a lot of them are really just have simple intuitions. I think it's very important for you to understand and get the intuition or at least memorize some of these properties. Right. So without further ado, let's get ourselves started. Right. So let's start with the exponential distribution. So recall that we do have the PDF form of the exponential distribution, right? So x belongs to exponential. We call that the theta. If we have our CDF, like cumulative distribution function, has this form, 1 minus e to the negative theta x if x greater than 0, otherwise 0 otherwise. Just recall that the CDF is really just the probability x greater than equal to x, right? So because of the CDF, then we are also able to, like as we discussed the last time, this is the CDF. We also can calculate the PDF. PDF is really just when we take the derivative of x, it's really just that 1 minus e to the negative theta x and dx, d to dx, right? So you do a bit of the derivative, you get this form theta e to the negative theta x. Right. So in general, you can sort of think that the theta is a scaling factor. It's really just the standard one. Like you can really just to get the intuition you memorize. Usually you memorize the setting for theta equal to 1, then fx. Right. This is called fx. Right. Equal to when theta equal to 1. Then this has this very nice form, right? So if you do the integration of e to the negative x dx 0 to infinite, you get 1, right? So this is a very nice, right? So you can also see that if we want to get an exponential random variable of theta, what we really need to do is to get this exponential random variable of 1, and then it's divided by theta. So then you will be able to get the then that's actually the same as exponential random variable of theta, right? So this is the reason that this is a scaling factor. A lot of time when we want to get the intuition, we just set theta equal to 1, right? So last time we do have this the memoryless property. I'm not going to prove that this property again, but let me just recall that, right? So probability of x greater than s plus t condition on x greater t is the same as probability of x greater than s, right? So regardless how long you wait, you need to wait the same amount of time to see the next the end of the exponential process, right? You really you can think about that as waiting for buses, regardless how long you wait for the same bus. Like if you model the waiting time as the exponential distribution, then you need to wait the same amount of time. Right. So we are not going to prove that. So the first thing we're going to prove about is really just that it's the minimum of the multiple exponential distribution, right? So let x1, x2 up to xn be exponential distribution such that x1 has parameter theta 1, x2 has parameter theta 2, and xn has parameter theta n, right? So there are two properties we want to talk about here. The first property is that I want to talk about the mean of all of them, x1, x2 up to xn. This is really just the theta. This is equal to the sum of theta. Equal to 1 to n, right? So in the special case, there are two let's just memorize the two special cases, right? The first special case is the mean of x1, x2 is the same as the theta 1 plus theta 2, and the second special case, this is special case 1. Second special case would be just the mean of multiple thetas that are identical, right? So if I assume theta 1 equal to theta n, right? So this is the n times theta, right? So what's the implication here, right? So Well, before I talk about the implication, actually let me also write down the second property we want. The second property I want is related to the order statistics. Minimum of x1 up to xn equal to xi is the same as theta I divided by the sum of theta I less than theta, I less than n. Right? So let's talk about the implication, right? So let's still imagine that we are waiting for buses. Right? So I actually have, for instance, I have two routes I can use, right? One is the route, I'm just making things out, route 1, this is for route 2. There are two buses I can use. Let's assume that the inter-arrival time for bus 1 is modeled by the exponential process, exponential theta 1, and this is the bus 1. And let me change a different color, right? So this is the bus 2, right? So this is another bus we can use. This is arrival time. The inter-arrival time is modeled as exponential theta 2. Right. So let me just be more specific, right? So probability that that the next bus, route 1 arrives follows exponential distribution of parameter theta 1, and similarly the probability of the bus that the route 2 arrives follows distribution of exponential theta 2. Right. So let's first look into the specifically what does that mean for having only one bus. For having only one bus basically says that my expected waiting time, right? So let's say this is the T1, is really just 1 over theta 1. So basically when theta 1 goes up, your waiting time goes down, right? The wait time, right? So let's imagine that my theta 1 is usually is 10 minutes. This would be some realistic estimate or approximate of a lot of buses you are waiting for, especially for larger cities, right? So, and similarly, if I talk about the waiting time for the second one, it's theta 2, right? So again, you can sort of see that theta 2 goes up, then the waiting time goes down. Right. Now we are saying that so long as one of these two buses arrive, then I can go home, right? So basically, so in this case, then the expected waiting time for me to go home is really just the T1, T2, and following using the claim we are making here, right? So the mean of these numbers, it's actually still follows an exponential distribution, and the parameters becomes the sum of them. So so that when I take the mean here, it's really another exponential distribution. So I shouldn't say the expectation, right? So this is the mean of this random variable. The significance says that if I take the mean, it's another exponential random variable with parameter theta 1 plus theta 2, right? So so if I take the expectation, right, so T1, T2, then basically I want to take the expectation of the exponential random variable theta 1 plus theta 2. Let me just use the formula again, theta 1 plus theta 2, right? Right. So so I think I was a bit too quick. Like, let me just clarify a few issues here, right? So when I say mean equal to this one, it's just now I missed that. The mean itself really has two properties. The first property is it's still an exponential random variable. Right? I take the mean of a set of exponential random variable, it's still exponential random variable. The second property is that if I look at the parameter, it's the sum of them. Sorry that I wasn't able to clearly state that just now, and here I also say that I want the 1 over theta 1 to be 10 minutes, right? So let's call that 10. So basically theta 1 is going to be 0.1, right? So, and let's also assume that the 1 over theta 2 to be 10 minutes, right? So that really just means that theta 2 equal to 0.1. Right. Let's do a bit of a calculation. What would be the expected time for me to wait until at least one of them arrives? Right. So theta 1 is 0.1, theta 2 is 0.1. I sum them up. 1 divided by this is 5. Right. So what's the intuition here? Right. So if I have two buses here, right. So the two buses here, buses is 2. Where is my bus? Right. If I have two buses here, if the expected waiting time for the first one is 10 minutes. And then for the second one, it's also 10 minutes. And if I just need to wait until any one of them arrived, my expected waiting time is shortened by a half, right? It's 5 minutes, right? So it's more or less matching your intuition that if you have two options for going home, then usually your waiting time is halved. So the second implication here is that it's talking about that, well, under this particular setting, it's that what's the probability of mean of T1, T2 equal to T1, right? So this is what we can calculate. The physical meaning, the meaning associated with the bus story is that, well, if I wait until one of the buses arrived, what's the probability the bus is T1, is the first bus or the second bus? Right, so in this particular setting, of course, like by symmetric, right, so their arrival time are the same, it's both 0.1, so basically with half of the probability I see bus 1 and half of the probability I see bus 2, right? So but now let's just modify these parameters a little bit. This is 0.2, like basically 0.2 means that the number, the waiting time here becomes smaller, like first bus arrives more frequently, right? So if we look at this setting, and then we plug in the what we get, the conclusion we have, the theorem statement is mean of T1, T2 equal to T1 if it's really just the theta1 plus theta2. In our case, it's 0.2 divided 0.1 plus 0.2. It's 2 over 3, right? So it's intuitively right? So it's everything is very intuitive. It's that there are 2 times more buses of the route 1 compared to the route 2. So the probability I use the first pass is probably 2 times more than the probability I use the second route, right? So because if I look at the same thing as T1, T2 equal to T2, right? It's of course like it's 3, 1, right? So this number over here is 2 times larger than this number here. It's matching the intuition that, well, I have 2 times more buses and for the first type than the second type, right? So it's 2 times more likely that I get the first route. Right, so that's the interpretation here, right? So now let's prove that, right? So prove that, right? So proof, right? So basically, it suffices to really just we only need to prove the x1, x2 cases, right? So in general, we don't if we need to prove we need x1 up to xn, the general cases, then we can sort of do that by induction, right? So now we want to say that this is what we need, right? So it's the mean of x1, x2 follows an exponential distribution of theta1 plus theta2, right? So again, like here you need to be a bit careful, and when I write exp here, a lot of times before this lecture, right, it's we referring to an exponential function, right? Here it refers to a random variable with a specific parameter, right? So be a bit careful here, right? So now, how do we prove that, right? So we sort of want to compute compute the PDF, the CDF or CDF or PDF, or whatever thing that's characterizing this parameter, right? It turns out that this is sort of related to when we talk the mean, it's sort of related to order statistics. Right? Usually the most straightforward way is to compute the probability of mean of x1, x2 greater than equal to x, right? So if we compute this one, then we sort of like it's the same as then we are able to compute the probability of mean of x1, x2 less than equal to x, right? So because this 2 term, right, sums up to 1. This 2 term sums up to 1, right? So less than, right? It's the same, like it's the measure of 0 at x, but let's be a bit careful here, right? So that's and a lot of time it's really just simply easier to calculate this term. The reason is that it's the same as the probability of x1 greater than equal to x and x2 greater than equal to x, right? So just notice that the statement here is the same as the statement here. x1, x2 greater than equal to x. They are the equivalent, right? So this is actually one of the most major devices we can use when we talk about this kind of order statistics, Right. So when we have this kind of AND operations, x1 and x2 are independent, then basically we can get this out. x1 greater than equal to x, probability of x2 greater than equal to x, right? So we can just plug in did a bit of calculation and realize that this is e exponential to negative theta 1 x, and this is exponential to negative theta 2 x. Right. So how do we do that? It's really just that it's 1 minus f probability of x1 less than x, right? So this is right, just that by the definition we have, like, just recall that we have fx equal to 1 minus this e to the negative theta x when x is greater than equal to 0, 0 otherwise, right? So I'm copying the whole things out, right? So this fx is really just here. Right, so let me just change it, turn here, right? This term is the same as this term, which is the same as this term, right? So it becomes 1 minus, so e to the negative theta x, right? So that's the reason these things get cancelled, that we get the product of these two terms out, right? So as soon as you get the product of these two terms out, it really looks very nicely, theta 1 plus the theta 2 and x, right? So now you can see that this is actually exactly the same as the situation, that probability of the exponential random variable theta 1 plus the theta 2 greater than equal to x. That's the reason we can sort of see that the mean of these two random variables are still an exponential distribution with the parameters being the sum of them, right? So this is important. That's the reason that we call this sum after we do a bit of calculation, right? Right. So now let's see that how do we generalize that, is at least for this part, right? So to generalize that, what would be the mean of x1, x2, x3, right? So it's, as I said, we can really just prove by induction. It's really just equal to the mean of x1, x2, and x3, right? So this again are equivalent, but we sort of see that this is actually an exponential random variable with the parameters being the sum of them, right? So, and then this is x3, right? So this is the reason that we can simplify that a bit, but like, let's again just use the same result, that the mean of two exponential random variable, this is exponential theta 3, right? The mean of the two exponential random variable is still an exponential random variable with the parameters being their sum, and that's the reason that we can keep doing the same thing to prove the general case, even for up to xn. So this is the first part, and the second part, we also just want to start with the probability of the mean equal to x1, x2 equal to x1 is the same as theta 1 divided by theta 1 plus theta 2. Right? So again, like, you can sort of see that once we have this result, this is what we need. Once we have this result, we can easily generalize to n variable case. Easily, right? So that's the reason. Let's just stick to this one, right? So when we want to stick to this one, then so basically, in order to get this out, it seems that there's not too much tools that are available. We just do calculus patiently, right? So probability of mean of x1, x2. Is equal to x1. This implies that probability of x1 less than x2, right? So let's really just do the straightforward calculation, integration. So x2 can move from 0 to infinite. In this case, x1 can move to 0 to x2, right? Because I need x1 to be smaller than x2, right? And I have this x1, x2, right? This is the joint PDF of x1, x2, right? I'm going to go back to this very soon, right? x1, dx1, dx2, right? So now we sort of also, like, this is the f x1, x2 is actually the same as f x1 times f x2, right? So of course it has different parameters, right? So these are the PDF for the joint distribution, and this is the PDF of the first one, the PDF of the second one, because of the independence. So we can sort of express that into a product form, right? So we really just recall that this term here is the theta 1 e to the negative theta 1 x, and theta 2 e to the negative theta 2 x, right? So basically this is what we got, the f x1, x2 that's connecting to here can be expressed in this term. Right. So now let's really just write down everything again. X2 equal to 0, infinite x1 equal to 0 to x2, x1, theta 1, theta 2, e to the negative theta 1 plus the theta 2, x dx1 dx2. Right. Oh, actually, I cannot do this. Sorry. So I need to be a bit careful. Right. So this is theta 1, x1, x2, right? So e to the theta 1, x1 minus the theta 2, x2. I cannot merge these two terms. Right. So now we can also do the integration of the x1 first, everything that's related to x1, right? So basically, let's pull out this x1 equal to 0 to x2 theta 1 e to the negative theta 1 x1 dx1, right? So this is everything related to x1. And let's the rest of the term, right? So we have put this term to here and this little term to here, right? So this term, the rest of the terms are this term over here and this term's over here, right? So we can just write this theta 2 e to the negative theta 2 x2, right? And then 0 to infinite, right? Let's also write x2, just make this clear. And this is dx1, dx2. Right, so this is the integrations we are talking about, right? So when we integrate this one, this is again like just a pretty straightforward integration. Let me not go into details. At the end of the day, we get 1 minus e to the negative theta 1 x2, right? So I integrate x1 and with the upper bound being x2. So after the integration, it's a function of x2. Right, so now let's put the parenthesis here, theta 2 e to the negative theta 2 x2, integrate from 0 to infinite dx2. Right. So again, this is sort of the pretty straightforward integration that's happening here. Right. So so let's see let's also simplify that a little bit. We will get this as theta 2 e to the negative theta 2 x2 minus theta 2 e to the theta 1 plus the theta 2 x2. This is the integration we want to do. And basically, let's see whether I can explain this in a little bit details. Right. So this is so actually, there's not much things we can do. Theta 2 e to the right. So basically, so now let's not go into that. It's a simple calculus exercise. Eventually, like it's up to here. You just need to recognize that it's calculatable. Right? So at the end, right? So I skip this calculus exercise, and then it's throughout this course. I don't expect you to calculate, do heavy calculus operations. If you're doing that, maybe you're not using the right approach. Referring to the homework and finals. But for the examples and the lectures, sometimes we go through that. We just assume that we are able to do that. But I don't anticipate that you are able to do that. You need to do that in most of the homeworks and finals, right? So that's the reason that we are able to go through the direct calculus to be able to prove that this is what we need, right? So the whole story like we care most about is that how do you move around, manipulate the CDF, translate the CDF into the calculus form, and after you transform that, like you need to recognize there are some independence going on, and then you are able to move around the term. At the end of the day, it will just be a straightforward I guess a straightforward calculus without too much probability interpretation. Before this, like a number of steps before that are actually interpretable in probability languages, and that's the reason we go through that, right? So now, after this x1, x2, as I mentioned, that like you can generalize that to x1 up to xn, but I'm not going to talk about that for the generalization. It's pretty straightforward. Right. So now that's pretty much it for the exponential distribution, right? So that's actually a pretty simple one. So now we want to be able to talk about a Poisson process, right? Right. So a Poisson process is used to model the arrival of events, a number of events, right? So again, I just assume this is time interval, and this would be just t1, t2, t3, all the way to ti, all the way ti plus 1, right? So these are really just saying that at time t1, certain things happen, right? So that could be the arrival of buses, that could be a patient is admitted to the hospitals, and then these are the arrival time, and then we want to be able to have a process to describe, to count the number of events that's happening there, right? So basically we want to use something called nt to count the number of events that happened in the period between 0 to t, right? So let me call this as t, right? So I want to a stochastic process to model how these events arrive one by one. And in order to characterize this process, you want to use that, like, let me fix a t, and let me try to fix this interval. This is 0, this is t. I want to count the number of points that are here, right? That's our definition of nt. Right. So now we are going to talk about a very specific way to construct this process that has a lot of nice properties, and that's also heavily used in real world modeling. That's what we call the Poisson process. Right. So as the name suggests, like Poisson process, it's sort of closely related to the Poisson random variables we learned earlier. Right. So I'm at the definition 8.84. Right. So a Poisson process is with parameter lambda is a stochastic counting process, and t is what we call the stochastic counting process. This is the stochastic counting process. Right. And such that it has 4 properties, right? So the first one is n0 equal to 0, right? So we start with counting to 0. And the second one is the so-called independence and stationary increment. Right. So that really just means that, like, for any t and s greater than 0, we have the nt plus s minus ns is the same as nt, right? What does that mean, right? So let me look into, let's say this is the time interval here, this is my s, and then this is my t here, right? So my nt minus plus s minus ns is really just the counting the number of events that's falling into this small red interval, right? So this counting is saying that this is equal to nt, right? The little t here, right? So basically the number of events that's falling into this red interval would be the same, like, in terms of distribution, than the number of events that falls into this purple interval, so long as this is also t. Right, so this is what this independence and this is what the independent incremental is talking about, right? So in addition, right? So we are talking about independent and identical incremental, right? So that's talking about, like, that we need another independence that's like for any two disjoint intervals, t1, t2, and t3, t4, right? So n of t2 minus t1, n of t2, let me just be careful. N of t2 minus n of t1 is independent to n of t4 minus n of t3. Right, what does that mean? Again, like, let me just draw something. Like, let's say t1, t2, t3, t4, t1, t2. Let me just also draw a little bit to make sure that, like, this you don't accidentally think they are of the same length, right? So it's saying that if I count the number of events that's happening here, the pink one, and the number of events that are happening here, those are independent. right? This is saying that regardless how many events that happened here, it's even there are a lot of events happens here. That doesn't imply that there are smaller amount of this kind of events happen in this interval, right? So in terms of the patient admission to the hospital, like regardless of how many patients you were admitted last night, it's not going to impact the number of patients you are going to admit tonight, right? So this is not a realistic property. Probably it's not realistic, but it's often at the same time good enough for a lot of modeling questions, right? So this is the first two property. Let's talk about the next two properties about the density, right? So it's the density basically says that the probability t goes to infinite and t divided by greater than equal to 1, it's divided by t, it's number, right? Goes to 0, right? So that basically means what does that mean, right? So if you look at infinitesimal small area, right? So basically it says that if this is t, right? So when t is around 0, then when t increases, the probability that I see one event also increases in a linear manner, right? So it's basically saying that if I want to talk about how the number of event changes at least when t is 0, so this is nt, right? So the derivative, right, the first order term is number, right? So let me just repeat, right? So when t is sufficiently small, then the probability that I see exactly one event is proportional to t, linearly proportional to t, right? So p is small, but when you scale up a little bit, then the chance you see one more event, exactly one event is number, right? So now the fourth property is that the limit t greater than less than, this is also the same time that t tends to 0, t probability, and t greater equal than 2, it's 0. It says that it's so long as the t is small, then it's very unlikely that within the same very small interval, two events happen at the same time. Right. So actually, this four property is sufficient. So let's see again what are these four properties are talking about. So it first says that like I start counting with 0. The second property says that I want some sort of some of the most natural independence assumptions we are making here. And the third and fourth one is saying that, well, I want some ratio, I want some rate that's controlling the rate, especially when t is small, right? So, and then I want some linearities, especially I want the linearities, like for the case that probability nt equal to 1. Right. So now it turns out it's pretty interesting to see that with these four properties, we are able to show that to get the exact characterization of the distribution of nt.